First, thanks for inviting me. I'm very excited
Recording in
to talk about this.
progress.
This is pretty new stuff. So I'm going to talk about the interaction of relativistic light with wavelength scale objects. I'll first start with acknowledgements to the team. So it's a collaboration between our group in Tel Aviv and Alexia Rifiev's group in UCSD and the group at Slack. So I'm going to just give just a small introduction to the laboratory in Tel Aviv, and then just formulate the problem and tell you about the experiments where we irradiated the isolated microbars, and then talk about the what we found out. And this is divided into two areas: the emission mechanism for electrons from very small objects, and their following in their interaction over large propagation distance in vacuum. Okay, so the laboratory in Tel Aviv is, we started out about 6 years ago. We have a 20 terawatt laser system, 500 microjoule, 25 femtosecond. About 8 graduate students, and we rely a lot on undergrad students' help. The laser is the traditional TISAF laser, except that the front end is a picosecond OPCPA, which gives us a fantastic contrast of about 10 to the 11 at minus 70 picosecond. The laboratory is divided into 3 experimental areas. In one of them, we're doing surface harmonics. On the other is the irradiation of solid targets in what we call high repetition rate, meaning 10 hertz. And on the third one, we're generating harmonics from gas targets. And the idea is to do coherent diffractive imaging or lensless imaging. Okay, so this is kind of a 20-year-old riddle. So in maybe more than a dozen different experiments, people have noticed that whenever you have some micrometric or smaller than micrometric roughness on the surface, being nanowires or, there's a couple of examples, nanowires or plastic spheres, or some formations of waters that you naturally grow under vacuum. There is one observation on all of them. The coupling of laser energy to all of these objects and the emission of radiation is much higher when the surface has some roughness versus when it's flat. So all of these results, the example of the results below show either the absorption of energy or of laser energy or the emission of X-ray or the emission of protons. I'm not sure if you can see my pointer. But all of those are showing the difference between a flat surface and a rough surface, and the characteristic is the same. There is more radiation emission, and the absorption is completely different when the surface is rough. Now, of course, there are many suggested explanations in the literature. Some of them has to do with the local enhancements of the fields, due to the accumulation of charge on the tips of those structures. Some of them has to do with various extensions to Brunel heating, to vacuum heating, whether the extension of the surface area or just giving more available trajectories for the electrons to be heated. But the point is that the current data is lacking in identifying the complete explanation. I would just, since I think that we're going to hear a lot about this in Laszlo's talk tomorrow, so I will just point out to this experiment, which gave a lot of new information, where the radiation of single isolated tungsten nanotips for the first time showed the characteristic angular divergence of the emitted electrons. But I will not say nothing about it, just encourage everyone to come to Laszlo's talk tomorrow morning. Okay, so here is how we approach the problem. We managed to fabricate micrometric gold wires They are suspended over a large distance, large enough that we can fit the laser focus in it and irradiate something which has, at least in 2 dimensions, it's smaller than the wavelength. So this is a project by Michal. She's a very talented PhD student. And what we're seeing here is first the microscope image of those wires. They are suspended over a gap in a silicon holder. What you're seeing in the right are microscope images with that 10x magnification, but this is already in the experimental chamber. And if I'll turn on this animation, this is Michal showing how she can move the wire around. So the dark part here is a gap. She's looking through the gap. And this is a 1 micron thick rod or bar or a micro wire suspended over this gap. And Michal can move around the wire. She can move around the laser focus in low power, make sure that they overlap, and then take the shot. And the parameters that we can play with here are the dimensions of those microbars and the relative angle to the polarization of the incoming laser. So the striking result is that the same phenomena that has been observed in random formations of some rough surface is exactly replicated in for a single object. So what we're seeing here is the emission of the spectrum of the emitted electrons from three different type of objects in 0 degree, meaning the electrons going in the laser direction. And what we are comparing here is the radiation of a gold foil, so something which is infinite in both the transverse directions, 200 nanometer thick, versus a micro rod, which is also 200 nanometer thick, but in 1 dimension, it has the scale of the wavelength. So in this case, 2 micron. And here we see that there is very low spectral emission of electrons for the foil. And for this rod, when the radiation is in S polarization, meaning that the electric field is parallel to the long dimension of this microbar. But when we rotate the microbar in 90 degrees, suddenly everything lights up and lots of electrons with much higher spectrum. The real big surprise comes from the angular distribution of the emitted electrons. And what we're seeing here, so this is all in the p-polarization mode. And these are angularly resolved spectrograms. So we see that the electrons, those hot electrons, are emitted in a very collimated way in 2 jets with a very small opening angle, something like 2 or 3 degrees. What we're seeing here are the results for different width of the rod, going from 2 micron to 6 micron. Here are above each spectrogram, we see the microscope image of the rod prior to irradiation with the spot. And we see that so the emission is in the MEV range. It's in 2 jets with small opening angle. And we see that it's also of a very narrow energy range. Something cuts it from the bottom and from the top. So these are the experimental observation. This is the information that is now open for interpretation. And the interpretation is divided into 2 parts. We start with the emission mechanism. So I'm going to show here a 2D particle in cell simulation taken with the epoch code. I'm going to start the animation in a second, but expect to see the laser coming from left to right. The blue to red color scale is the transverse electric field. And the gray object in the middle, this is the micro rod where we are looking at it from the top. So this is a 2D simulation. And we also asked the code to color high energy electrons in green. So electrons with energy above 2 MeV would be colored in green. So here is the laser pulse coming. And we see bunches of hot electrons in green. I'm going to play it a couple of times that you can notice it, going with a very small opening angle, and they are bunched every half optical cycle, and they emitted right at the peak of the pulse. Okay. So here is the same simulation here at the bottom. So it's p-polarized light. Here is 1, 2, 3, 4, 5 time frames. We'll see those green electrons emitted every half optical cycle. And as a control experiment, we run exactly the same simulation, but on an infinite target on a foil. And we see that on the foil, the laser pulse propagates, creates some plasma and reflected back. No hot electrons versus this microbar situation where those are electron bunches are emitted every half optical cycle. So what's going on here? And I think that the nice thing here is that you don't need more than first year electromagnetism to understand the emission mechanism. So it is an extension for vacuum heating. So in vacuum heating, the longitudinal component of the laser field. So here we see exactly the same simulation, but now I'm plotting in the red to blue color scale. At the top row, the longitudinal field. On the middle row, the transverse electric field, and at the bottom row, the magnetic field. And we'll see, we're looking at four different, on four time frames. So we see that exactly as we learned in the graduate studies about vacuum heating, the longitudinal component of the electric field pulls and pushes electrons every half optical cycle. The transverse field gives them a transverse motion, but for an extended target, for large flat surfaces, this has no consequences. The electrons are being pushed transversely, maybe a little bit, but they are immediately pushed back when the optical cycle switches, after half an optical cycle, where the laser field switches signs are being pushed into the material. But in a small micrometric object, electrons which are emitted very near the one of the edges of the target have the opportunity to go around the object. And this is due to the combined action of the electric field that pushes them forward, and also the cyclotron motion induced by the magnetic field. So what we're seeing is that those green bunches are these electrons that manage to be born very close to the edge, manage to circumvent it and propagate into vacuum. Now, this is nice. This could be the whole story, but it isn't, because there are a couple of experimental observations that are not, this emission mechanism is not sufficient to explain. So if we look again on the summary of what we know now, so we see that the emission indeed happens every half optical cycle. It will generate two jets with an opening angle, but the opening angle here is actually not that small. In the experiment, we're measuring angles of something like 2 or 3 degrees. The emission angles here, if we just stop the simulation and measure them, are much larger. And the question is, what happens? What happens between the emission and until the time that the electrons reach the spectrometer? We need to find some explanation for these 3 observations: the separation, this small separation angle, the fact that the spectrum is cut from the top and from the bottom. And also, if we look carefully, there is some positive correlation between the angle and the energy of the electrons. So to do that, we asked the simulation to follow up on the electrons for a much larger distance. And here in 3 colors, we see the angular resolved spectrum of the same simulation, but after sampling it after 1 Rayleigh range or 2 Rayleigh ranges or 3 Rayleigh ranges, and we see that the angular resolved spectrum evolve over a very large distance. This is Rayleigh range here is something like 40 micron. So this is already 100 micron into vacuum, and the spectrum and the angle and the angle of the emission changes. Now, this is a pretty bad thing to follow up on particle in cell. It's very, very computationally expensive. And the low statistics here that I marked in with the circle, it's as an indication that something here is very expensive. So instead, we rely on the observation that those attosecond duration electron bunches maintain their very short duration. And for us, this is an indication that the space charge forces between the electrons in each bunch are negligible. So to try and figure out what really goes on, we gave up the particle in cell and just switched to a simple particle pusher, meaning simulating the fields, the action of the fields on just a single electron. So first of all, you have to find the right electron to be able to analytically model the electric field. And this is not that hard. If you take just a Gaussian beam and calculate an obscured Gaussian beam, taking one beam and subtracting the shadow in a complex way and calculating the fields, we immediately recreate the diffraction pattern of an obscured Gaussian. And the important thing here is that the diffraction pattern is such is that there are dark channels. So this is just a two-dimensional slice, but this low intensity stripes here was actually interpretation is that there is some cone with low fields propagating over a very large distance. And once we have the field, we can start throwing electrons at it and just in a finite difference method calculates the trajectories for the electrons. So this is a tool. I'm going to show some results. You're going to see on the right side, you're going to see the magnitude of the electric field in green, going from 0 to some arbitrary number. The more informative part is the left plot, which will show the direction of the electric field in some interesting color code. So I'm going to start the simulation and let it run a couple of times. What you would see overlaid on these fields are electrons, which were injected into this simulation. And the color indicates their initial energy. So between 4 in black and 9 in white MEV. And you see that immediately that the trajectories are interesting. And now we want to try and figure out what's going on, what happened to them during this propagation of one Rayleigh range. So the first thing I would draw your attention at is that on the left plot, the white slivers, everywhere which is white, means that the electric field points backwards, meaning that electrons will be pushed forward. So when interpreting that, wherever you see a white area, it means that the electrons are being accelerated, electrons there would be accelerated forward. And the interesting thing about this diffraction pattern is that if you notice those white slivers in the center, this is at the shadow of the object, they diminish. So after about one Rayleigh range, which is 30, 40 microns, they completely disappear. So let's follow up on those electrons. First of all, we have to determine where to inject them. And we take the injection point from the particle in cell. So we follow up a couple of optical cycles following the radiation. We find the location of those electron bunches, and this is where we inject them into the particle pusher type simulation. And then following up on them a little bit, we see that at some distance, they manage to be trapped in one of those white slivers up until some point here, a couple of microns following the radiation, where the sliver becomes, this accelerating volume becomes too small and they slip away. When they slip away, so a lot of things happen, but in general, they slip in phase with respect to the laser. Nothing is pushing them forward anymore. But electrons at this energy range that we picked for the simulation between 4 and 9 MeV, after some time, find themselves trapped again in another forward accelerating volume, another white sliver. And this is what we're seeing here. Now, letting them run a little bit more, we see that some of them manage to stay in the channel in this low energy accelerating structure. But if the electrons were too fast or too small, the relative phase slippage with respect to the laser poles pushes them either to the inner or outer edge of this low field channel, and immediately the strong transverse fields push them out. So only electrons of a very narrow energy range, in this simulation, this is orange, so something like 6-7 MeV, manage to stay in the low field channel. So here again, this is the same simulation, and just plotted over a couple of time frames between x equals 0 and 35 microns. This is one Rayleigh range. And we see all of those parts of the journeys that we just described in words. And what we're seeing here at the on the right is with the same color code, the final emission angle and the final energy. So going over these final results, we see first that indeed this mechanism explains the trapping of a narrow energy range. Everything below some energy threshold or above some energy threshold is just being pushed out by the transverse fields. We see the low divergence angle, very close to 2-3 degrees as we observe the experiment. We also see the positive energy to angle correlation. And an interesting conclusion that we can get from this code is that those electrons were actually accelerated forward. So this low field diffraction channel is acting as an accelerating structure. And we think that this could be very interesting for some engineering of more sophisticated accelerating methods. Okay, so some conclusions. The experimental observations were that the small jet separation angle, the high and low energy cutoff, and the correlation between angle and energy. All of those have been being recreated in both in the particle in cell and in the simple particle pusher loop. If we look at the evolution with wider and wider rods, so there are two observations in the experiment. The opening angle gets larger and larger, and the electron energies are diminishing, and this is also recreated in the peak. So to summarize, we're trying to find an answer to a 20-year-old outstanding question. Why do rough objects interact so differently with relativistic laser pulses? And the way we attack the problem is by radiating isolated, we call them micro rods or micro bars. We see that it's very polarization dependent, and we understand why. And all of the emission characteristic we measure in the lab can be explained by a two-step process. First has to do with the emission, which is a simple extension to Brunel heating for small objects, and then by all kinds of effects that happen when the electrons interact with a laser field over a very large distance in the vacuum. So, thank you.
Thanks, Ishai. Very interesting. And are there any questions? Yeah, Laszlo.
Hi, really interesting results. I recognize many of the results which are similarities to our electrons from nanotips. I have two questions, at least I have many, but let's say just asking two. First, your simulation showed quite nice agreement, but the electron energy, if I saw that well, there is at least a factor of 10 difference. Mm-hmm. Did I saw that well, and what is the reason for that?
Yeah, so it's due to two effects. One of them, two reasons. One of them, the intensity in the simulation was much higher. We actually, the simulations are expensive, so we wanted to simulate exactly the laser intensity in the lab. but then we found out that we didn't account very carefully to the transmission. Anyway, so the first reason is that the intensity in the simulation was very high, and the second one is it's a 2D simulation, and there are a bunch of known effects which results in lower energies in 2D simulation versus a 3D world. Here specifically, we suspect that in a 3D case, electrons have much more opportunities to be ejected out of the accelerating.
I see. I assume you use the Gaussian beam in the simulations.
Yes.
Mm-hmm. And maybe a second question. You showed these white areas, what you claimed is the accelerating phase. Why is this not half an optical cycle? I mean, the electric field is changing every half an optical cycle.
Yeah, let me...
I mean, it was, as I saw, much narrower, much shorter than half an optical cycle. Yeah, exactly here.
Here? So, yeah, maybe I'll show them together with the laser field. Could be easier. I guess it's a little bit hard to show. Let's see. Okay. So, yeah, so an optical cycle here would be, let's say, yeah, so it's easier to see on the intensity, on the electric field strength, on the green scale. So an optical cycle here would be something like, yeah, it's 800 nanometers. So an optical cycle here goes from white through black and again to white.
Exactly. Mm-hmm.
And they switches direction in the positive and negative directions of Y, as we see in the peak, where the electron bunches are also switched every half optical cycle.
Yeah, but if I understood you well, you mentioned that only this white area between the red and the blue is accelerating.
Accelerating forward, yeah. Black means that it's actually decelerating.
And red or blue?
Here on the angle. So it's kind of the angular scale is plotted here on the left. This is a way to show. We had to find some color schemes that would show a 360-degree angle, but what's really important is what's forward and what's backward, which is white and black.
So this is not the electric field. Okay, I see.
The angle of the electric field.
Okay, I see. Yeah, that is definitely influences the phase velocity, and that is important. Really interesting results. Congratulations.
Thank you.
Thanks.
Okay. Anyone else? Because maybe I have a quick question from an ignorant. Okay, I'm not in this field, but if I look at these green electron bunches, they seem to be very short in time. Do we have an estimate of what was the duration of these bunches?
Yeah, so first of all, I have to say that Laszlo worked much more on the analysis of the temporal characteristic. Again, I don't want to step on his talk tomorrow, but when you're doing it with much shorter pulses, few cycles, then you get a bunch of opportunities on what to do them. But Laszlo, maybe you can correct it, but these are tens to 100 attoseconds.
I would say on the order of 100 to 300 attoseconds. You can see that the distance between two green is 1 optical period, so 2.7 femtosecond. And it is maybe 1/10 of it.
Yeah. So interesting to use them for stuff, right? A lot of stuff.
I have a hunch that Laszlo is going to talk about it tomorrow.
Okay. No, that's very interesting. All right. If there are any other final questions or comments? Okay, so thank you, Ishay, again, and very interesting area and results. So okay, we can move on to the next talk, which will be given by Emmanuel Dumier, which will be talking to us about investigating transverse and longitudinal ion acceleration using ultra-intensity fused cycle shortwave laser pulses.
So, hello, just to be sure, can you see my screen?
Yeah.
And it's full screen?
Yeah.
Perfect. And just, is it changing?
Yeah.
So, okay. Okay, so hello everybody, I'm Emmanuel Dumier from the University of Bordeaux, and today I will talk about, as it said in the title, about ion acceleration, but also so ion acceleration using fused cycle lasers, but also how we can produce these fused cycle lasers, especially for very high photon energies, so for small wavelengths. So just I want to present my colleagues. So the results I will show were obtained in the framework of a collaboration between Cilia at the University of Bordeaux and École Polytechnique. So first I will present a brief, I will review some results from other colleagues who showed the interest in using fused cycle laser pulses for particle acceleration in general, and in particular for laser ion acceleration. Then I will discuss how we can obtain experimentally this kind of pulses. Then I will show the simulation and theoretical study we have performed of the interaction of high energy attosecond pulses with proton boron targets. With just a quick discussion of how we could apply this to proton boron fusion. And for this proton boron fusion, it's more the transverse and acceleration that is of interest. And so after I will discuss briefly the efficiency of using fused cycle pulses for longitudinal proton acceleration in this regime. And finally, I will discuss the influence of the laser wavelength for fused cycle laser pulses. So first, as I said, I wanted to review some recent results that were obtained with first experimentally on this slide, and then more with particle insert simulations on the next slide using fused cycle pulses. So here, I wanted to show the results of that were obtained by a group from INRS near Montreal in Canada, where they focused very tightly fused cycle pulses, which is of longer wavelengths than we used to. So it's 1.8 microns. This is a very small energy pulse, 7 millijoules. And the duration is 12 femtoseconds. So at this wavelength, it's roughly 2 optical cycles. And they focused it in air. And what they were able to obtain MEV electrons in the process. And so what it showed is their main interest was to show that when you start to concentrate too much laser energy, you need to be careful about radiation issues. Even at low laser energy. And but it also showed that if you are able to focus very tightly and use only a few cycles, so therefore you can, even with low laser energy, get to high intensities, you can get into the relativistic regime. So it was quite a nice result, which is now published. And about the interaction of fused cycle pulses for this time for laser ion acceleration. There were also publications in the recent years. I just took 2 of them. On the left, you have some 3D particle insert simulation results from Wu et al., which were published in POP in 2021, which here you have the proton spectra. The different colors correspond to different pulse duration. And the laser energy is kept constant. And what we can see is that in their simulation, which were for kind of thin foil, the parameters are here, There is an optimum in laser pulse duration, which was for this particular set of parameters, 3 laser periods for laser ion acceleration. So there is something to explore when you're trying to optimize the laser ion acceleration for a given energy budget in trying to shorten it to few cycles. And more recently, so this is a PR article from 2023. So LPHYS et al. From LPHYS published an interesting study where they looked at the interaction of few cycle laser pulses. So here you have the parameters. So it was 8 femtosecond at 5 × 10⁻⁹ watt per square centimeters, focused on 5 micron. They did 2D peak simulation of the interaction of these pulses with gas jets, and they were able to obtain, so here the energies are not incredible for the protons, but compared to the energy in the pulse, this was quite efficient, and as it's using gas jets, could be interesting for some applications requiring high repetition rates. So there is a push right now to go to these few cycle pulses. And so on the experimental side, one way to go to such pulses is to use thin film compression. So it's a technique proposed by Gérard Mourou et al. And developed more recently by Kazanov et al. So the idea is to use a usual, usually it's around 10 cycle near-infrared laser, to make it go through a thin film, which will broaden its spectrum, and then to use a compression mirror that will compress all the wavelength to reduce duration pulse. So there were nice experiments that were performed at INRS a few years ago, where they were able to go from 25 femtoseconds to something like 12 or 14 femtoseconds. And so more recently, the group of Daniel Gruszewski and Gabriel Beotu at LINP did similar studies at Apollon on the long focal area, and also at LINP, where they were able to also to observe a shortening of the laser pulse. So for now, it's still not theoretically it can go to a single cycle compression. For now, we're still at few cycle compression, but these were promising results. And so we are now working on adapting this setup for the Apollon short focal area setup in a collaboration with team of Julian Fuchs, LINP, and INRS. And we also got beam time accepted at INRS on their short focal area. So that's what I presented in the previous slide, is a way to get to few cycle pulses, but still staying in the near infrared. And if you want to go to shorter wavelengths, a solution is first to do the first stage I described, to try to obtain a single cycle if it's possible, or at least a few cycle pulse. And then to focus this single cycle pulse on a plasma mirror to generate harmonics. And the lower the number of optical cycles interacting with the plasma mirror, the shortest attosecond bunch you can create. So this was a scheme already proposed by Natalia Namrova in 2004. And so our end goal is to do the full chain. Of course, for now, we're more at the first stage experimentally. And in the next step, we'll go to the creation of this single cycle, low wavelength pulses. There have been some simulations on this part. I'm not going to detail all the results, but already in 2021, in a Journal of Physics paper, the setup that I described in the previous slide, so the second stage was simulated, and the results are what we see on the left. And so when sending a single cycle femtosecond lasers, they were able to reflect this kind of half cycle, they call it half cycle because of the duration attosecond pulse. And this is a pulse result spatially. And so one thing to keep in mind for its perspective of my talk also is that this is just the isolation of the attosecond pulse, but of course you're also going to reflect some near-infrared signal. So in fact, there will be a superposition of these pulses. One way to avoid this and if you're still not capable of obtaining few cycles of attosecond pulse, what they propose also is to use a near critical density plasma in front of the plasma mirror to shape the incoming laser. And if you choose well the parameters of this near critical density plasma, you can shape it so that this is what we see here. You will mostly get the interaction of single cycle near-infrared pulse that will be able to create this single cycle attosecond pulse here. So these are just simulations, of course, and this will need to be explored experimentally. Just as an alternative, there is another possibility. It's to not just create one attosecond pulse, but to create a train of attosecond pulse using classical high harmonic generation, which is illustrated here, or even if we could also use the setup proposed by Henry Vincenti, where the idea is that if your laser intensity is high enough, you're going to curve the reflecting surface of the plasma mirror. And so you can also even focus your harmonics. So these are the kind of background in where we're doing our study. Just to illustrate this on a kind of summary of various sources available, why we're very interested in these attosecond pulses is because if you look at this classification of sources as a function of peak power and decreasing wavelength, you see that in this energetic infrared pulses part, there are a lot of sources, but energetic attosecond pulses, that's Terra incognita. So we have performed some simulation of these pulses, first on proton-boron target. So this is the setup. The simulations here were performed by Rémi Capdessus while he was a postdoc at Syria. And the wavelength is 10 nanometer. The normalized amplitude is 140. It's focused on 10 lambda. And what is interesting with these pulses is that even a solid proton-boron target is actually transparent. It is at 3% of the critical density for this wavelength. And so you're able to study the propagation of UV-X range pulse in a solid. A very intense one. So the simulations were performed with EPOC. So here you have some example of results. Here's the electron density at an early time where the laser is starting to create a channel in the proton-boron target. At these early times, we see that we have efficient acceleration of electrons. And for now, at this early time, it's mostly transverse acceleration of protons and boron ions. So because you have the energy on the y-axis and the angle of emission on the x-axis. You also get high energy photon, but not that many, because we're in a regime where the radiation reaction effects are not that important. So electrons are swept out of the channel. We accelerate proton and boron ions transversely. And this can be of interest for some applications, because if you look at this slide, so what we show is the proton density in two cases. On the left, you have a case with just one optical cycle in the laser pulse, with 1 joule of total laser energy. And we compare it to a 10 joule case. So all the parameters are kept the same, except here we go to the duration is 10 optical cycles. And what we see, so it's at two different times. And so I showed already that the laser is going to carve an electron channel void of electrons. And ions are going to be, transverse, large amplitude transverse electrostatic or electric fields that will accelerate the protons transversely. And we see the accumulation of density that is happening on the side. And if we calculate the velocity, we can also look at the proton phase space. We see that we can go to velocities around 10% of the velocity of light in the transverse direction. And another interesting aspect is that, in fact, even if we have 10 times more laser energy in this case, for this transverse acceleration, the one optical cycle case is more interesting. It's more efficient. And so what we have done is we have looked at the application. So these were 2D simulations. So you have to imagine that in 3D, it would be a radial acceleration of these ions transversely. And so what we wanted to see is, as it's a proton boron target, we wanted to see how many alpha reactions or how many energy we can convert to alphas. And this is, of course, in the framework of the interest on electronic fusion with proton-boron fusion. Here is just a reminder of the cross-sections for DT, DD, and proton-boron. It's very hard. It's not feasible for now to do it with thermonuclear fusion because the max of the cross-section is very high for proton-boron. And so the idea would be to go to impact or kinetic fusion. And the interest would be that there are no neutrons or few neutrons produced. And so we have calculated the production of alpha particles using Monte Carlo simulation, starting from our peak simulation results. And what we get is that, so here you use this kind of the setup. You have the channel, which is void of electrons, and the surrounding proton-boron solid. And in fact, the place where you have more alpha particle creation is the channel, because the cross-section is higher in this case. And not the cross-section, sorry. So the stopping of the particle is going to be favorable for the production of alpha particles. And so here, these are estimations of the energy transferred to alpha particles for our 10 joule pulse. And so it's not even 1 millijoule in the surrounding proton-boron solid, whereas it is 0.3 joule in the channel, which is, we're not very far from getting any gain, but which are quite interesting results for first test in this region. So these results were reported in this publication by Xavier Ribert. And now in the next part, I want to focus on longitudinal proton acceleration. So with the same parameters. So here we're looking at later times compared to what I was showing earlier. And what I want to compare is again a 10 cycle case and a 1 cycle case. So these results that I'm showing here on this slide are for a 10 cycle case. Here you have the energy spectra for carbon, protons, and electrons. And here's a proton phase space. And so here we are getting already efficient proton acceleration. But if we go to the 1 joule single cycle case, again, the efficiency is much higher. So we get almost up to 250 MeV with on the right, the corresponding proton phase space. So I don't want you, the thing to remember is not the exact number of the energy. These are 2D simulations. They are they should overestimate strongly the results that we get experimentally. But the idea is to show you again the importance or the efficiency of going to these single cycle cases. And so we studied, I won't have time to go in all the detail, but we studied just going to go back just to show you why it's more efficient in the single cycle case. And in fact, as we can see here, in the 10 cycle case, everything is very symmetrical. In the case of the 1 cycle case, the electrons are going to feel a kick during the propagation of the laser in the target, which will strongly depend in time and which cannot be averaged over multiple cycles. This is a very strong kick, so it will create a strong transverse acceleration of electrons and then of the ions. And there is strong heating also, strong acceleration of the electrons in the longitudinal direction, and there will be strong field accelerating the ions. And so it's really, there is an advantage is that the scaling of the electron energy and of the ion proton longitudinal and transverse energy is better in the single cycle case, but it is at the cost of the symmetry of the process. That's also something which is important. I will come back in the perspectives on this. And so just to finish, I just want to I won't have time, but I wanted just to show here the maximum proton energy spatial distribution in the single cycle case versus the 10 cycle case at a given time. And it is mostly to show that in the single cycle case where we get very efficient acceleration, the acceleration starts from inside the target. And so what we're going to get is, for the accelerating mechanism, is a combination of a pressure push, the launch of a kind of shock inside the target. And of course, after there is a strong second stage of expansion that leads to these high energies, and that creates this wide energy spread, large energy spread energy spectrum. So we are we still continue to look at this regime, and we are looking at different wavelengths also, intermediate wavelength between this very short wavelength and the usual ones we are used to for the lasers we have in the lab. And here is just an example, so we're also looking still at this transverse acceleration for proton-boron fusion. And this is another example where here you have the transverse phase space of protons in a single cycle case and a 10 cycle case, this time as 50 nanometers, where we found exactly the same features, where we have this asymmetry in the single cycle case with much faster transverse expansions than in the 10 cycle case, even though it has 10 times more energy, laser energy in this case. I just wanted to discuss briefly here. I talked a lot about the interaction of attosecond pulses with matter. In fact, you can find more or less exactly the same acceleration processes. It scales well with the wavelength. So if here this slide is, if we think about what it would require to do a single cycle pulse, so at a wavelength of 10 microns, like we could have on CO2 lasers. So here the A0 equal 140 would correspond to 2.7 10 to 20 watt per square centimeters. The single cycle is 33 femto. And the target we used in the previous simulation would correspond to a 500 micron target with a density of 3.3 10 to 17. So it's a gas jet density. And so here the difficulty for this wavelength would be to create sharp gradients target with the gas jet. We could go to a kind of intermediate regime with mid-infrared lasers. I'm not going to go over all the parameters, but basically the laser energy you need to get exactly the same acceleration I showed you, it will scale as lambda, the wavelength for a single cycle pulse focused at a given A0 on a given number of wavelengths. And also, a second advantage of going to lower wavelength would be that sharp gradient under this target will be much easier to produce for these small wavelengths. So, to conclude, I wanted to show that there is a strong interest right now in the interaction of few cycle pulses for secondary sources. That we can accelerate efficiently ions, as it was already shown at very near infrared pulse in several publications, but we show also that at much smaller wavelengths, these single cycle pulses can efficiently accelerate ions both longitudinally and transversally. There is still a lot of work to do. First, on the generation of the required laser pulse. We're working hard on the first part, to do thin film compression, and we hope with the NRS experiments to get to shorter, to few cycle laser pulses, and to show the interest still in the near infrared for an acceleration experimentally. We're going to go on the simulation side to 3D simulations. There are things that are not realistic or that we need to be careful about in our simulations. That's a question I mentioned about the superposition of the near infrared pulse with the attosecond pulse in most of the setups I presented to produce attosecond pulses. There is sensitivities to the CEP. I did not show it, but I focus mostly on ions. But these pulses are also very interesting to accelerate high energy photons. So Florent Brun in the framework of his PhD is looking at this. And it had been already, so there were already other. The idea would be to create very short gamma pulses, like it was proposed using other technique, like in the Li et al. Paper PRL from 2015, and to be able to do more realistic prediction about the proton-boron fusion application, we will need to go to integrated multi-scale numerical simulation, not just to simulate the first part with a P code, but to look at the expansion of the transverse ion pistons that we created and see if it can continue or not to produce alphas while it propagates brightly. Thank you for your attention.
Hi, thanks, Emmanuel. Any questions?
Sure. So,
yeah, Laszlo.
It's a really interesting. Thank you very much. It was a really interesting talk, and I'm really happy to see applications of few cyclopulses in different fields like ions as well. Though I recognize one point, and I'm not sure that the comparison is quite fair, is the 10 cyclopulse, namely for the CH target, and probably this is valid for other comparisons that you showed before, that you took a time 10 femtoseconds after the start of the simulation, which is definitely much longer than the single cycle pulse. The single cycle pulse paused completely, while it is not even the half of the 10 cycle pulse. That means the 10 cycle pulse didn't even reach the maximum intensity.
So it's true for both, in fact, because it's 10, here the wavelength is 50 nanometers. And so the laser period is 3.3 divided by 20. So it's going to, we're much past the, so 3.3 divided by, the interaction is finished 1.5 femtosecond. So there is small vacuum to propagate, but basically it's passed for both.
I see.
So this is like more the long-term effect on the target. The interaction is finished. And here it's more thinking about this proton-boron application. We're trying to see the dynamic of this radial piston, because the idea would be, we would be interested to see if it goes to a collisionless shock. And using other code, we would like to see how this collisionless shock would again evolve on even longer time scales.
It's a good comment, because this is concerned by my second question. I mean, fusion, you speak about fusion. There, it's typically you have to heat it up a lot and then keep it together. But in fact, you are just concerning the speed of the shock. But if, I mean, you generate a shock and after the laser has left, will this be really some source for fusion, or the shock is then propagates away and that's all? So you understand that now these 10 nanosecond lasers are used and they're long, while here you just use a few femtosecond laser.
Yeah, because they try to do thermonuclear fusion. It would be, we cannot heat it. So the peak, main peak of the PB cross section is 600 keVs, and so it's totally unfeasible with the nanosecond lasers we have. We will need several hundreds of megajoules to do PB thermonuclear fusion. So the idea here is to see if there is a way, a more, they call it impact fusion or kinetic fusion. So the idea would be to see if we can set up a kind of chain reaction which would still let out more energy than we brought, like liberate more energy through alpha. Here we're very far from it, because for now we're like at 3% efficiency, and with very optimistic predictions. But still, over these short times, there is a real possibility that the kind of radial pistons that we're seeing, here it's fast, it's several tenths of the velocity of light. So on its way, it's going to create PB reaction, proton-boron fusion reactions. So this, we're sure that we're going to have many proton-boron fusion reactions being created. What we're not sure about is that we're going to produce more energy through these reactions that we're investing.
I see. Thank you.
And Ishai?
Yeah, so the range of the MEV alphas in those targets is not very long. So at what point do you need to start including in the simulation the propagation of the fusion alphas?
So
heating.
This would be the next step. It could help a little bit because it would heat locally, so it would deposit some energy in the path of this radial shock or piston and then shock, for instance. But the problem here, I'm still doubtful about any scheme showing realistic proton-boron fusion perspective, because for me there are no real paths to a real chain reaction like you can have for DT, where you are going to liberate alphas, and the alphas are going to heat, and they will be able to launch new DT fusion reaction. Here, the alphas we are going to deposit, they are never going to heat the plasma locally to 600 keV or to be able to launch new PB reactions themselves. So I don't want to be too pessimistic about proton-boron fusion, but because we're still looking at some aspects of it. But yeah, I don't see a clear path for now. But when I said we need a multi-scale integrated numerical simulation, that's one of the, what you're mentioning, the alpha transport is one of the bricks we need to put.
Mm-hmm.
Okay. If there are other final comments or questions, I don't see any. All right, so let's thank Emmanuel. Ben, thank you very much. So for the final talk of the session, so this was supposed to be delivered by Elias Gersmeyer, but is currently busy in an experiment. So he passed the slides to me. So if you don't mind, I'll present that on his behalf, because members of the same collaboration anyway. So I'll try my best to represent Elias on these. So I'll just share the slides quickly here. So I'm not gonna introduce myself. So the talk is on a slightly different topic. So now we are talking of a new detector that we have developed for high field physics experiments. And this is a gamma ray spectrometer, which is able to operate at high flux and at high energy, so GeV and above. And it's a single shot spectrometer, so it doesn't need accumulation. And we believe that this is a detector of interest for measuring gamma ray beams generated, for instance, during high field QAD experiments, such as I'm thinking of nonlinear Compton scattering. So one of the motivations for developing detectors of this kind is high field QAD experiments, and one of these experiments currently planned is the LPHYS' experiment, which is planned to take place at the UXFEL. And the idea is to take the 16.5 GeV electron beam from the accelerator and interact it with a relatively high intensity laser, so a laser power of 300 terawatt in the first phase. We have seen earlier today that one of the main limitations of these high field QAD experiments is the shot-to-shot reproducibility and quality of the laser wake field electron beam. So one way around it is to bypass the wake field mechanism and use accelerate electron beams from a conventional accelerator, which are of course much more stable and reliable. And LPHYS is one of these projects. It's not the only one. There's also E320 in Slack, for example. And one of the main diagnostics of the experiment is a gamma ray to look at the spectral distribution of gamma rays emerging from inverse Compton scattering in the laser field. So, for instance, if you look at simulations of what the of these gamma rays is expected to be, for instance, if you interact a 16.5 GeV electron beam with a laser of different intensities, so here you have different colors correspond to different laser intensities, and this psi is A naught or eta, depending on how you want to call it, but it's the dimensionless laser intensity. So you see the known gamma ray spectra that you would expect with the Compton edge and nonlinearities, and of course there's a lot of physics that you can unveil that you can study in the gamma ray spectra. So for instance, you have the shifts in Compton edges due to the electron mass stressing in the laser field. You have nonlinearities, so multiphoton Compton scattering, and you can study the level of nonlinearity of the scattering. But as you may know, it's very challenging to obtain spectral information or high resolution information for high flux and high energy photon beams. So one idea is to take these photon beams, back convert them into electron-positron pairs using a thin converter target, measure the spectrum of the electron-positron pairs, and then use the Bethe-Heitler cross-section to deconvolve the electron-positron spectrum and retrieve the original gamma ray spectrum. So to test a detector of this kind, we went to the Apollon laser facility, and here you have a sketch of the experimental setup that we adopted, and the main results are also available in this paper on the archive if you're interested. But in a nutshell, we use the Apollon laser, focused it with an F60 spherical mirror onto a gas cell to produce broadband electron beams with a peak maximum energy of the order of 1.7 GeV. And then these electrons were interacting with a solid target to generate Bremsstrahlung radiation, Bremsstrahlung photons, and here you have the expected Bremsstrahlung spectrum from this interaction. Then we had a dipole magnet to get rid of, or basically to separate the electrons and positrons from the main gamma ray Bremsstrahlung beam, which then entered the spectrometer itself. So the spectrometer consisted of a converter target, 200 micron or so tantalum, to generate electron-positron pairs, some collimators, and then a magnet to separate the electrons and positrons from the main gamma ray beam. And this is the spectrum that you would expect to measure in the detector. So this is some experimental data. So if you look at the signal that you record on the Lanex, on the scintillator at the end of the spectrometer, you have the main gamma ray straight through, which is this rectangular bright spot. And it's rectangular simply because that was the shape of the collimator that we are using. And then on either side, you get the signal that you're interested in, which is the electrons and positrons on either side of it. And this signal disappears if you take the converter out. So if you background subtract the signal, you get these two regions of signal on either side of the gamma, so the positrons and electrons, and of course these should be in principle identical. And these are some example, 8 consecutive shots. These are experimental data of the electron-positron spectra that we measure at the end of the spectrometer. So once you have these electron-positron spectra, you can use them to infer, or if you want to deconvolve these spectra to get the original gamma ray spectrum that was incident on the spectrometer. So this is basically how you would calculate electron-positron pair production in a solid target. So you have the d sigma over dE would be your Bethe-Eitler cross section. dN over d omega is the gamma ray spectrum. So basically here we need to invert this equation, because we do measure the electron-positron spectra, so dN plus minus, and we want to by inverting this relation, obtain the gamma ray spectrum. So this turns out to be not to be an easy inversion problem, because the kernel of this operation is a lower triangular, and therefore is quite generally ill-conditioned for inversion. So a direct inversion is not really very precise, cannot really be trusted. So instead, we used a Bayesian approach that basically tries to invert globally the relation. And here are some examples, some numerical modeling of what it looks like and how it performs if you assume a Gaussian photon beam or a step-like photon beam spectrum. And as you can see from simulations, it's actually quite accurate in reproducing the gamma ray spectrum, and it has quite high resolution, especially in resolving edges, as you're interested in Compton scattering, with energy resolution, for instance, for LPHYS of the order of a few percent. So we applied this method to our experimental data, and here you see some examples, some 8 consecutive shots, where on orange, you have the convolution of the gamma ray signal experimentally obtained. The dashed line is the expected signal from simulation. So you see there's quite good agreement across for the 8 different shots. And 2 interesting things of this detector is that it's a single shot, so you don't need to do accumulation, so you're not sensitive to shot-to-shot fluctuations in the experiment. And also we demonstrate you can perform long time operations, so there's no real ablation of the converter target. So skip that, it's not too important. So in conclusion, we performed the first experimental tests of a gamma ray spectrometer designed to work at the GeV level and with high flux. And we're using the Apollon laser facility, and we believe this could be a key diagnostic for the next generation of high field QED experiments, because it allows you to resolve the spectrum of inverse Compton scattered photons, which carries a lot of information on the interaction. And it could also be used for future photon-photon experiments where you use Bremsstrahlung radiation and laser fields to generate pairs. The experiment confirmed the possibility that this could be used on a single shot, so it's insensitive to shot-to-shot fluctuations, and also it can be run for long periods of operation, as expected, for instance, for LPHYS. So it allows you to acquire high statistic data. The resolution is of the order of 20% at the GeV level, but it's expected to scale strongly with energy. So for a multi-GeV experiment such as LPHYS, this is supposed to go down to a few percent. So apologies if Elias could not be present. I hope I did reasonably well to represent him. Thanks very much for your attention, and if you have any questions, they're more than welcome. So I'll pass it to the chair of the session, which is myself. Any questions? Yeah, Ishai.
So I guess there's a lot of optimization to do with the thickness of the radiator, of the converter.
Yeah, that is correct, because too thin and you don't have much signal, and too thick and you start to have scattering and
lose resolution.
And loss
So
of resolution.
my question is this trade-off is a limiting factor in the context of experiments like LPHYS'? I mean, do you might be constrained by resolution because the radiator has to be that thick?
Yeah. So for the happy medium, for LPHYS' is around 200 microns, and of high Z tantalum, just because it's sturdy and resists longer than ablates less actually than lead for these gamma ray signals. And we in our modeling we do include scattering, but at these sort of thicknesses it doesn't seem to be particularly important, especially because you have to consider that we have very high energy photons, so it's GeV plus between 1 and 10 GeV. So scattering is usually quite negligible.
So the radiation length is much longer than the radiator.
Yeah. It's
okay.
Yeah. Eva?
Thank you for that talk. That was very interesting. Is there a way that you might be able to adapt this so that you can also get out the polarization of the gamma radiation?
In principle, yes. And this is something that we are looking into because it's extremely interesting, extremely important. From the preliminary studies that we have done, I can tell you that it's actually not that easy. But it's definitely something. Yeah, you're right. It's definitely something worth looking into, and we are looking into that. It's tricky, but not impossible. So, hopefully.
Okay, well, good to know. Sounds interesting. Thank you.
Yeah, Christoph.
Yeah, I also like to stress. I mean, we have done a lot of calculation, like from looking at the polarization that you can infer information about the dynamics and so on. I think so. We would be very excited if this polarization is seen. But what I also wanted to ask, I mean, I understood that LPHYS' has a few political problems. So can you adapt this also for other experiments? I mean, to use this, I guess would be used for many other experiments, right? So not just so.
Absolutely, yeah. So I've shown LPHYS' because that was the main motivator at the start. To start developing a detector of this kind.
What do you have to change something or what?
Yeah, so the more important thing is that the size, the physical size of the spectrometer, the size of the magnets and everything else scales with the energy of the photons that you're looking at. So if anything, going down in photon energy makes it a little bit easier because it shrinks the size of the magnets and everything else. The spectrometer that we fielded in Apollon is in fact much smaller it's basically a rescaled version of what we planned for LPHYS'. Now, that said, there is another limitation, which is if you go and look at lower energy photons in the range maybe hundreds of MeV or GeV, which is expected from, let's say, ELI-like experiments, at least in the first stage, you lose a little bit in terms of spectral resolution because as you know perfectly well, the higher the photon energy, the more collision electron-positron pairs are generated. Therefore, the higher the spectral resolution you can get. So if you go down in energy, you can still use it, but the resolution goes down a little bit. For instance, for 1 GeV photons, like in LPHYS', like in Apollon, the energy resolution was of the order of 20%, which is good, but not great, and it can be improved. But definitely, it is scalable. It can be implemented in smaller scale experiments. Definitely.
Gianluca, I'm very glad to see these results. That's about you mentioned about gamma ray flash experiments. And you see that we made a lot of simulations of gamma ray flashes, and we are doing this. And typical energy, not typical, but cutoff energy of the order of 1 GeV. That is why your method hits perfectly.
Yeah. This can definitely be implemented for experiments of this kind. Yeah, it'd be nice to have, I mean, if this is published or if there's something, it'd be nice to try some of the spectra that you expect and see how they would behave in our detector, just to see what, you know, how we can measure them and with what precision. But
maybe I missed what you presented. Have you calculated with Monte Carlo simulation? You used Fluke? What?
Yeah. And we also did the experimental test in Apollon, but we do have the full model. Yeah, we do have the full Monte Carlo modeling and the inversion algorithms so we can try, we can just see. It'd be interesting to see what we, you know, if this could be measured and with what resolution and so on. But I don't see any problem, to be honest.
Yeah, great. Thank you.
Okay, I think we're actually on time. Yeah. Okay, well, that's good. All right, so let's thank myself again.
Well done, speaker.
And so, okay, so this is the end of this session. So we'll restart tomorrow at 8 Universal Time. Whatever that means, or Greenwich Mean Time, and Sebastian Cordy will be the chair for that session. So thank you very much for attending. Great talks and pleasure to see you all.
Excellent session. See you tomorrow.
See you tomorrow.
See you
Bye. Bye.
Thank you. Bye.
Bye.
Thank you, Christoph.
Yes, welcome.